Okay. So today I will be drawing a lot on the whiteboard. So you guys, if you are kind of a little bit on the back, you can sit closer so you will see more. We have to review some of the concepts before I will dive into assignment 2 details. Okay. So if you open YouTube and you press upload video, what is happening? So can someone kind of guide me through what is happening when I say upload a video on YouTube and the video is being uploaded? What will happen if I close this tab? Yeah?
Depends on how YouTube has implemented.
So I have this progress bar here. It's kind of saying, 10% uploaded. Upload, and we are on YouTube, and I'm uploading a video, and I clicked close this tab. What will happen? Yeah?
I assume a signal will be sent to the browser saying, please close this down, and it can respond by saying, okay, I don't want to close down, or it can be forced to close down, and if it forces, then it would stop the upload, and it might even save the progress that it has done, so that if you try to do it again, then it will start from that specific time slot.
Okay, so there is a lot of different things that can happen, right?
Yeah.
So the thing that actually happens is they write here, do not close this tab while the video is uploading, right? And if you click close this tab, it just closes and your video stops being uploaded, and you have a partially uploaded video to that point, and that's it. If you go back and you try to upload the remaining, you have to start over. So effectively, you have to go there, delete what you've uploaded, and kind of re-upload it, right? So it's kind of inefficient. But the point here is that there is a piece of functionality on the client side, and the client side is reading the file from your local file system, and the client communicates. So go back there. The client communicates with the server to push the data, and then once you shut down the client bit, the whole thing stops working, right? Is it clear? So you cannot upload the file if this middle bit is missing, right? So the client has some code which reads from your local file system, encodes the data to be passed to the server, and then it passes it through. And it takes a while, right? Okay, what will happen if you have a client code which connects to a service? So let's say let's use Fixer, right? So we connect to a Fixer, we ask Fixer for something, and then the reply doesn't come. What will happen? We will have a timeout, right? So the connection will time out, and then we will get kind of an error code saying, no response, right? So we kind of connected to a server, we ask something, and then we never got anything back. So after some time, we will time out, and we will have an error situation, okay? So if you can have a timeout on the server side, but you can also have a timeout on the client side. So on whichever end of connection you're trying to get something and it doesn't come, after some time you have to kind of cancel it, right? So with this one, with the second model, right? If I connect to a service which takes a very long time to generate the answer and then send it back to me, what will happen if I connect to a working service, I ask a question, and the service takes a long time to generate the answer and then send it to me? It didn't crash, it's just working, but what will happen in this situation? In the situation 2, we never got the response. In situation 3, what will happen? It's pretty much the same as situation 2. We will time out at some point, right? So how come we connected the client to a server and we uploading the file, and let's say it takes 8 hours to do this, and the connection never really times out. Why is that happening? Yeah?
Because you split it up in small chunks and send small bits at a time.
That's right. So what you could do is, instead of having the connection open all the time, statefully, you open a connection, you send a small chunk of data over, you close the connection, and then you open it again, send some data over, and close it, right? You could do that. But what's the problem with this? Yeah?
Overhead.
There is an overhead, of course. We have to initiate the resources, initiate the connection, and so on. So it's not ideal, right? So we can keep the HTTP connection alive for an extended period of time as long as the client and the server agrees that that's what they want to do, right? So the timeouting is kind of a default behavior. But if I connect to a server and the server sends me back a header saying, keep this connection alive, the data is coming, it just takes a long time for me to generate the answer, then the client will not time out the server, and the connection will stay alive for as long as both parties need it to have alive, right? In fact, you can have it alive for days, right? So as long as you have the tab open and the connection is established and kept alive, you can kind of have it going on forever, okay? So with this third option, where we connect it and it takes long time for the service to give us an answer, what we need to do is we need to send an initial header saying, well, you know, the data is coming, keep this connection alive, we are good, but it will take a while for us to generate the answer. So after this initial header, the client knows not to time out this session, and it will kind of keep it alive for as long as the server needs to generate the answer, okay? All right, so that was kind of a very quick review of the things that happen with HTTP and with the HTTP requests. So coming back to our YouTube, when we're reading the file and uploading it, obviously we have to have a piece of code which does the job. So if we shut this down, there is no piece of code which is doing that job, okay? But let's make a case where we've already uploaded it. So we've stopped reading it from the local file. And now, instead of upload window, you have a processing, right? So YouTube is now encoding your video to the streaming format and preparing it to be published on YouTube. While the processing is happening, again you have a progress bar. And again, what will happen if you quit that tab now? Yeah?
Nothing. You can come back and then we'll still be processing the data because now you're no longer streaming data, you're just waiting for you to process.
Exactly, perfect. So first thing you will notice is that this warning disappears, right? You're not uploading anymore, you're processing. And then YouTube says, well, while we're processing, you know, feel free to do whatever you want because you're not required anymore. The client code is not required. So if we close this, the server will continue doing what it's doing, okay? So now let's a quick look inside of what is happening, all right? So if I have my client code here, and initially I was making an HTTP request to upload the, I mean, we're using upload, but just imagine whatever you know, different function that we called, right? And here is our server land, right? On the server, what is happening is you have some sort of a service like what you've built for assignment 1 and assignment 2, and this service responds to HTTP requests, right? So for the initial part, the service is doing nothing. When the request comes, the server spawns a process, a thread, right? Thread is being started, and this thread kind of runs in a loop and processes the data that is coming in, okay? So it kind of reacted on the original request, and then, as I said, usually what you could do is you could send the header back saying, keep this connection alive, and then once the file is uploaded, it kind of, the connection is closed. So this thread is closed, right? So the thread which processes your request on the server land, so this is server side, is spawned upon request. And that was the upload case, right? What will happen if I close the client? Well, this incoming thing kind of blows up, so it kind of times out. Like I'm trying to read the next piece of data, I cannot get anything, so I'm timing out the client. I'm saying, well, it looks like the client just crashed or something, so then I will kill my thread and close everything, right, on the server side. If the connection was alive until the complete file was uploaded, I will finish it, I will finish this thread, wrap it up, and close the connection, right? So at the end of the process, I don't have this, and I don't have the connection anymore. I am able to request the next one. Hold this thought, because we'll come back to this. So the thing here to come back to is, what will happen if I have my service for uploading files, and I have 1 million people trying to upload a file to me, right? I have to be able to scale that service to spawn multiple threads and deal with multiple streams, right? But we'll discuss it in a minute. So now with the situation, with the second situation of processing, what happens is, so let's say I have this processing service. My video is being encoded. Who triggers that service? Is it the client side triggering that processing, or is it triggered internally by YouTube? What do you think?
By YouTube.
Internally by YouTube, of course, because once YouTube has this file, this video file, YouTube knows, okay, now we have to encode it and publish it, right? So it's internally triggered by the server side itself, right? So it is not initiated by HTTP request, it's initiated by something else. So what would fit in here? Well, that's the yeah, I will just keep writing here instead of using the screen, because you wouldn't be able to see the screen anyway. So we need some sort of middleware which will communicate to us events which then start some processes, right? So those processes here are kind of responsible for being triggered by the HTTP requests. Those processes here are triggered by some internal messaging or kind of queue system which initiates those threads, right? So this thread for uploading the file was started by the service or upon HTTP request. This thing is happening because I decided that this file is finished uploading, and now I have this file to be processed, so I injected something into the queue or something, like I raised some sort of notification, and then this process started a thread to process my file, and it is kind of internal. And then once this is done, it will probably notify again through some sort of messaging middleware that it's done, right? So I may have another service which is responsible for notifying the user how far along the way we are, right? So I have, if I go to this page now, like I close the window and I went there again, I will kind of see the UI telling me how far I am. And this service is responding to HTTP requests again. But the processing itself, it doesn't, right? So you see that kind of at least two types of processes which are on the server side. One which is responsible for HTTP requests, and another one which is internally triggered by some internal events. And this question mark here is usually either a queuing system, so you have some sort of a queue, or you have some sort of messaging system, messaging bus. On Amazon, if you were to use Amazon Cloud, the queuing system is called S, which stands for Simple Queuing System. And then messaging bus stands, acronym is SNS, and it stands for Simple Notification System, right? We're not gonna go in details with those two. There is a lot of open source solutions for both queuing and for messaging. It just fit into this integration layer, right? All of those fit in here to separate what you're doing upon requests from the outside, from the web through HTTP requests, and what you do internally, right? This kind of decoupling is happening either through queues or through messaging. I will just talk a little bit about these two, what the difference is, right? So what is the difference between the queue and what is the difference between messaging? Well, the queue is, you know, queues from data structures, right? A queue is a kind of a data structure where you put stuff in and read stuff out. And you can have priority queues, you can have queues where you put stuff at the back and read from the front, or you can have like stack, like queue where you put stuff in from the top, but you also read things from the top. So if I put item number 1 and item number 2, with the stack base, I will read number 2 first and number 1 second, right? So queues are kind of useful for certain things. And in the case of processing, using a queue system would probably work quite well because you have some sort of worker which takes an input, an undecoded file, decodes it, and that's the task of the worker which is doing the processing, right? So normally what would happen is you would have a queue, and then the internal system would be putting, okay, file number 1 is ready to be processed, and then if you have multiple of those happening at the same time, they kind of keep flowing in, file number 2, file number 3, and so on. And then you have some sort of a worker pool which checks, is there any job to do? And if there is, they will take it from the queue and start processing file number 1. And then if you have multiple workers, it will kind of try to take file number 2, and so on, and process it, right? So you have kind of incoming jobs and a worker which kind of consumes the jobs, does the job, and then notify either by a queue, like you can have another queue saying which files are now done. And then once this finishes, it says, okay, file 1 is done, it's processed, can be published. So you can have another service for like publishing videos on YouTube, which is again having an input queue of what files can be now published, and is kind of waiting for this queue to fill up, to have some items. So queues are kind of good, and what is interesting is that depending on what you're doing, you can have different strategies of dealing with the queue, right? So if I have 1 million of those services grabbing files from users, right, and I have my queue, multiple processes might want to put something into the queue at the same time. So the question is, do I care about the order in which those messages kind of come in, right? Do I care that the ordering is perfectly synchronized? That if one of the services finished by a fraction of a millisecond earlier, that this file gets into the queue first, or I don't care, right? Because if I do care, I have to slow down the inputs into the queue, right? And if I don't care, I can relax those constraints and I can allow more throughput going into my queue. Like things can come into the queue much faster. What's the difference? In Amazon, if you care about the ordering, you cannot do more than 300 requests per second, right? That's the limit of the synchronized queue of consuming events into the queue, right? So if I have 1 million things here and there is a lot of things happening at the same time, I'm limited to only being able to process 300 requests per second about my queue, which guarantees that things that were a little bit faster than others are always before the other, right? If I relax that constraint, if I say, well, actually, if this file finished uploading just a fraction of a millisecond later, earlier, and this one a little bit later, I actually don't care which one gets processed first into the queue, right? It doesn't matter. Like those things are sort of flexible. Then I can process much bigger number of requests per second than 300, okay? So depending on the constraints of your application, you can go with the relaxed queue or more strict ordering of the items in the queue. All right, so this is a very quick crash course on queuing. And then about messaging, yeah?
How much faster?
Millions of requests per second. So depending on the infrastructure, depending on the resources that you're kind of dealing with, you can do pretty much unlimited. Yeah.
Is there some part of the messaging that is serialized, so you can have more than 300 because of like clock speed or something?
Yeah, exactly. Yeah. So basically, what happens is they have to serialize the request in such a way that the requests have to be ordered and retain the ordering, and then the actual putting stuff into the queue happens, right?
So you can't multi-thread that?
No, exactly. So they cannot multi-thread it, and the queue's data structure needs to be locked, and only one process at the time can be accessing it and writing to it, right? If we take this constraint away, what happens is we have our queue, but we have a little bit of a messiness at the entry, and we can have multiple partial queues kind of being here, and then I can be kind of taking in a random way things from those multiple queues and putting them here, right? So I'm kind of doing best effort to have everything ordered relatively the same way, but because I kind of have multiple of those, and if I injected stuff a little bit earlier here, but this one ended up here, and a little bit later here, but that was the first item in that additional queue. When I'm consuming stuff here and putting in the final queue, I may take that first and then second, right? So I may reorder the actual things that happened in real life, and they will kind of be reordered in the final queue, right? But because I can have multiple of those, suddenly I can scale. I can accept much more than 300 requests per second as an input and have it handled, right? Whereas if I don't have this intermediate layer and I am forced to only use a single locked data structure, then I'm kind of slowing myself down because of that. Okay, so messaging is similar to queuing, but with messaging we are not restricted to a single data structure, right? With queues we sort of talk about the data structure where stuff comes in and stuff comes out, like for example, first in, first out. But with messaging, any architecture for notifying things works fine. So in fact, what we can do is we could have publish, subscribe type of architecture with messaging, where I have a channel, like a named channel, which kind of publishes some events, and then I can have multiple subscribers subscribing to it. And I can have different delivery mechanisms. So again, I can have a delivery mechanism which says, if I have a channel and I have multiple people consuming from it, right? So I have a channel, and then I have subscribers. I would like to have a policy that only one subscriber consumes a particular event, right? And that is, again, a little bit costly, right? I can, because then I have to guarantee that only one subscriber gets a particular event and nobody else gets the same event. So if I have jobs to do, and I want to use the messaging bus to distribute the jobs to workers, I usually want to do this, right? But you can have a policy which says at least one instead of only one, right? And suddenly with this policy, I'm much more flexible. I'm trying to only deliver one event to one subscriber, but if you relax the constraint, suddenly I can be much faster. I can be delivering events much faster to the subscribers. And then from time to time, it just happens that these two guys were so, there was some race conditioning or something, and both of them got the same event. And then you have to deal with it on the kind of logic layer, right, yourself. If you want to delegate this kind of constraint into the system, then it basically slows you down, or it's more costly, right? So in case of messaging bus with Amazon, if you want the strict semantics, if you want to say, I want certain guarantees, you basically pay more because they need to do more computing for you, right? If you say, I'm more relaxed, okay, at least one is fine, then you pay less per message, but you have to do a little bit of logic yourself because you may have a race condition and two workers may get the same job. And then what do you do, right? If two workers get the same file to be processed, well, it's like you don't want to double up the job. You have to somehow notify each other that this guy, is doing it so the other guy can die, can stop doing it, right? So in case of messaging, it just boils down to money. Like if you want the logic to be happening on Amazon, you pay a little bit more. If you want to take care of the logic yourself, you pay less per the messaging bus, but you have to do a little bit of logic yourself. These things on Amazon are quite well organized, and the first million requests on either of those is free. It's in the free tier, so you can kind of freely experiment with it. But as I said, there is a lot of solutions for that. Like RabbitMQ is one which is really good. There is other ways you can kind of do it yourself and fit in something in here. Okay, why are we spending time and why are we talking about this? Well, it brings us back to assignment 2, okay? So as you remember in assignment 2, you have two things to do, among other things. So one thing is you have to respond to HTTP requests and give the user the current, say, exchange rate, the current exchange rate of a currency, right? So you're kind of responding to HTTP requests. And how it is happening? It is happening by you writing a service, which is in this category, and it awaits somebody's asking it to do a function. It does the logic and sends the response back, right? That part is clear. All right, but you have another task to do. You have to check with the fixer of what the current rate is, current exchange rate is, and log it into a database, right? So you have to log into a database the exchange rates, right? You can do it inside the service. So when someone asks you, okay, what's the current exchange rate? Then you kind of go to fixer, you check what the current exchange rate is, you log it into a database, and then you send the response back, and you have it in the database for that day, okay? But what will happen if nobody asks you for 1 day about the exchange rate? What if nobody asks you for a month about the exchange rate for any of the currencies? Your code will never get triggered, so your code will never get executed, right? So if you put that logic of the second task into your service, you have no control of when it's happening and how to make it work, right? It's even worse. So let's say you put it into this service, and you've done it this way. You have, so what you've done is you kind of cheated. So you have your service, which does this. First, it checks if the timer is working. Let's call a timer a process which periodically checks with fixer and gets the currencies. Okay. So the first thing you do is you check if the timer is on. If it is not on, then you start it. Okay, and start it in a thread. So you have a thread which kind of is separate from your normal processing, which goes into Fixer, gets the currency exchange and stores it into your DB, and it kind of is separated from your logic. And then 3, you respond to the request, right? So to the original request that was in, right? And then you start this service on your service hosting infrastructure, and you yourself ask the server for the first time, what's the current rate? And by doing that, you trigger your background process, and then even though you respond back, your background process is kind of in the background and kind of periodically checks the database, right? Would that work? If you design a system this way and you yourself ask your service for the very first quote and triggered this background process, would that work? So who thinks it would work? Yep, who thinks it wouldn't work? Why you think it wouldn't work?
I think if you did it right, you could spawn a lot of checkers that check for updates.
No, but you only start it if it's not on. So you only start it once. So if there is a second request, you check if timer is on, then you do nothing, right? You don't spawn multiple things. It would work, right? In normal circumstances, it would work. So if you did it this way, it would actually work quite well. The problem is that you're deploying your stuff on Google or on Heroku or on another cloud platform, and they are optimized for handling HTTP requests, right? So what it means is they keep your code inactive. They don't run your code until there is a HTTP request which triggers the function. So they wait for an HTTP request to come in. They instantiate your stuff. They let it work, let it prepare the response. And the moment the HTTP connection is closed, they don't care about your code anymore, because that's how the web apps work, right? The web app is there as a piece of function which responds to a HTTP request, generate the response, and then can be, disposed, can be shut down, can be put to sleep. And that's actually what happens. So Heroku will put your stuff to sleep after the last request was happening. So they will let it kind of run for 30 minutes. And then if there was no HTTP request in 30 minutes in the free tier, they will basically put your VM to sleep. They will just shut it down. And they will wait. Like if nobody asks for anything for a day, they don't run your stuff for a day, right? So they optimize in the free tier to not have anything running in an unusable way for more than 30 minutes. So this solution wouldn't work on Heroku, because this solution would only work for 30 minutes and then it would kind of be put to sleep. Okay? So what we have to do? Well, we have to work around it. So the way Heroku works, again, I was planning to use the computer to kind of show you, but I didn't put the screen up, so I will kind of do it here. Heroku recognizes the need for different types of activities. So the first type of activity is a web app. Okay, and that's exactly what you've been doing so far. You've been generating a service, you've been packaging it up, and then you've been publishing it on Heroku, and you've been using this proc file, and you've been writing web, and you write your executable for the service, right? All of you have done it for assignment 1. Those of you who did assignment 1 on Heroku, right? Do you remember writing the proc file and saying web with the executable that needs to be run upon request? Exactly. That's the first type. So the first type is for the things that respond to HTTP requests. And that thing will be killed in free tier after 30 minutes of inactivity. So if somebody didn't poke the web server, Heroku decides, okay, let's wipe it to a sleep, and then if the HTTP request comes, we'll kind of wake up and bootstrap it. Okay. The second thing, they recognize that your stuff may need to spawn a worker which does something in the background, right? As with YouTube, you would have the initial file upload as the web app, as a kind of a normal web app, and then the file processing, you need a worker. You need some sort of process that happens for extended period of time in the background, which is triggered by either a queue or a message, and it kind of works in the background. It doesn't respond directly to HTTP requests, and that's called worker, right? So the worker is an executable which is invoked upon request from the internal app. The internal app can say, well, I have this file now, you need to encode it. So the worker would be, so again, in the proc file, you would call it a worker, and then you would say what's the executable and how it gets its input and where it puts in output. Usually, the input-output happens with either the database or internal file storage or whatever, right? It's kind of internal to your system. It doesn't talk to the outside world. It doesn't respond to HTTP requests. It responds to internal events, right? So that would be the second type. And then they have a third type. So sometimes you don't want the worker to be started from, because like with the web app currently, what we have a user. The user triggers the web app, right? So the user makes some sort of a request to HTTP request to the web app, and then the web app triggers some sort of a worker, right? So at the end of the chain, there is always a user kind of triggering something, right? Even though this happens here by a queue or a message, it is a result of user asking something, right? But sometimes you want the work to be started without the user. Sometimes you want to have the work to be started by time or by day, season or whatever, like, periodically, right? So you want the work to be started by some sort of a clock. So a clock triggers some sort of message or queue, and then the work happens, right? And that's the case with us. So in assignment 2, what we want at least once a day for the worker to check what's the current currency exchange from Fixer and store it in the database, right? So we really want this type of pattern, and this one is called clock. Normally what you do is you have a clock which generates either a message or a queue entry, and then you have a worker which responds to that, right? However, and that's how would you normally do it. You would write a simple clock which puts something into a queue once a day, and then you would have a worker which observes that queue, and if there is something in that queue, it would kind of respond and fetch the data from Fixer. But in the free tier on Heroku, so again on Heroku, in the free tier, you are only allowed to have 2 processes, right? You have allowed one web process and one kind of a work process. So if you were to have a clock which triggers a worker and your web app, it would come up with 3, because you would have a process for the clock, a process for the worker, and process for the web. So we can only do, we kind of have to have a clock functionality embedding the worker functionality in the clock, right? So we will have a model which says one web and one clock, right? So for assignment 2, you need 2 processes. You need your normal web app, which responds to HTTP requests and checks stuff from the database. It doesn't talk to Fixer at all. So your web app doesn't talk to Fixer, right? Your web app just talks to your database, gets the rate, and responds with the rate you have in the database. The functionality which talks to Fixer is inside a second executable, which will be inside the clock. So in your proc file, you will have two entries. One called web with your normal stuff, and one called clock with the thing which connects to Fixer, gets the rate, stores it in the database, and shuts down, right? And that one will kind of run in a loop. And I've tested it with a loop which was every 20 minutes to do it. I haven't tested it with something which is much larger than 30 minutes because I'm not sure if in the free tier they would kill me if I didn't do something for 30 minutes, right? So maybe the limit is that you have to kind of do it kind of every 20 minutes. But this definitely works because I've tried it out and I tested it and it works fine. There was a question?
The names in the profile, are they special names or is
Those are names of executables that are gonna be executed by Heroku.
the key?
The keywords here, yes, those are special names. Those are defined by Heroku. So the worker, web, and clock are the types of processes that you can run on Heroku. Yep.
I have a free worker that's doing something every 24 hours.
Yep. And it was working fine? Exact. That's perfect. So that means that the limit of 30 minutes only refers to the web process, not to the worker process. So in that case, you don't have to be limiting yourself to smaller periods. You can basically do as he did, like the whole day. Yeah?
But you don't need any libraries from Heroku to do it.
No,
You
no.
just use the normal Go
It's
time
exactly. It's just the normal Go, and I basically did it with just sleeping for a while. Did you use sleep? Yeah, and that works fine. You can use a timer from Go as well, but I felt just pure sleeping and having a loop which does it all the same way all over and over again is fine. Yeah.
So do you call the clock from the web application?
No. So when you have your proc file with those two entries, they will be bootstrapped by Heroku automatically. So your clock and your web app will be kind of instantiated by Heroku, and you don't need to call the clock from your web app. It just happens.
So then you, in the clock, you would say that it should update every base that is possible, not just the bases that have been requested by
That's
the
correct.
user.
That's correct. Yeah. But we did specify in the assignment that everything should have the euro as a base, right? Did we, Christopher?
No, that was not intended. Was that the intent?
Yeah. That's because if you were to base everything on those multiple currencies, that's a lot of it's a big giant matrix you would have to fetch every single time. All we need is just to say, I think it was euro, that you ask for this big table for euro, and that's what you store, and that's it. So your base is euro, and then you could do for all the currencies. It's just more work, but as a proof of concept, just having a single base works as well, right?
Okay.
Yeah.
Yeah, you have to be very explicit about it in the text.
Yeah. So we will check the assignment 2 text.
There's a lot of people who find it confusing now.
Yep. Fair enough. So we will double check it. The intent was not to make you work like monkeys a lot. If you know how to do it for one base, you will know how to do it for all the bases. Yeah.
But with one data set from euro to all the other currencies,
Yeah.
can you use math to get from the other currencies?
You can. Yes, exactly. It's basically the same, right?
I've done that, but I'm wondering when you're testing, my code might come up with floating points.
Inconsistencies.
Yeah. So
That's okay. Yeah.
The thing you just said, you were talking about going from one currency to another back to a third one. That thing is not actually possible because the way currencies actually work in the real world. In the real world, there is actually there could actually be delays between currencies. Currencies don't have a fixed relationship to each other. It's just a constant evening out of the value.
That is true. Yeah, that's correct. But if I asked, so I'm not talking about going to a third one. If I ask, okay, give me all the exchange between euro and all the currencies, right? and now you're asking, okay, what's the exchange rate between NOK and euro? It's basically, you know, the same, right? You cannot go from this one to this one through euro because, again, you're introducing some error, but you can do kind of a reverse checks to euro from all the currencies. Yep.
I still disagree because there are different costs for going one way versus going the other way, even between two currencies.
But I believe with Fixer you just have one.
Okay.
I think they only have one rate between a pair, and then they either report this way or this way, but it's like it's not two numbers. I think.
Realistic.
Yeah.
I think you're confusing potential with actual value. Because in like the stock market, you can have like you can actually try and sell something cheaper than the actual.
I know. So in the stock market and in the banks, usually what you get two values for buying and selling, right? So you have a kind of a spread. You have a roof and and the bottom of what the exchange rate looks like, and then on the reverse you also have the two numbers. But like if you use Google Exchange, for example, it reports just a single number. It just reports a ratio, right? And it's if you go this way or this way, it's always the same ratio. But it doesn't matter. Like we don't care about the intricacies of the financial markets. All we care is about the webhooks and yes. So the bottom line is when you're storing the data in your clock, you only need to do it for euro. So you ask for euro, you get the big table, and then you get the currency conversions between currencies and euro and currencies. If you want to go from NOK to something more exotic, then you would have to have this extra table as well, right? Yeah. Yes?
From euro to American dollars, it's 1.16 Fixer, but from dollars to euros, it's 0.86.
Yeah.
So there are two different values.
Yeah, of course. But if you divide, so if you divide 1 by 116, will you get the other number? So
I don't know.
you should.
Yep.
Exactly.
Close enough at least.
Yeah, exactly. So with, as I said, like the floating point inconsistencies don't matter that much, right? Okay, so let's have a break. And in the break, we have some master students who would like to ask you some questions and do a small, short experiment on you. So I will let them explain.
Is there